Hi, everyone. Welcome back to E54. Today, we're going to be going over lecture 9, and we'll be introducing phase diagrams. So the issues we want to address are when we combine two elements, we want to understand what equilibrium state or what structure for our material that we get. And in particular, you can think about defining this in a way that if we know the composition and the temperature of our material, can we predict how many phases we would get? What are the compositions of each phase? And then what's the relative balance or how much of each phase do we have? And just as an example of something I've showed you before, this is an example of a two-phase material. So it's mixing together nickel and copper. In this case, one of the phases is a solid solution. So it's just sort of randomly mixed in there. And there's the original lattice. And another one is this phase B, where we're having some sort of ordered structure that forms. Okay. The first thing we can do is make sure that we are on the same page and rigorously define a phase. And this is just a homogeneous portion of a system that has uniform physical and chemical characteristics. Okay. So a phase has the following characteristics. It has the same structure and atomic arrangement throughout. It has roughly the same composition and properties throughout. Now that roughly comes about from, for example, if we look at a solid solution, you can, of course, if you zoom in enough and find an individual atom or ion, that's going to be different than the atom next to it. But the point is if you look at some representative collection, so maybe you look at 100 atoms, then you're going to always see the same composition and properties. And the other and final characteristic we want to talk about is that you should have a definite interface between the phase you're talking about, any surrounding or adjoining phases. So just a few examples of things we could talk about and things that are relevant to E54. For example, iron is an element that we talked about. We can have either body-centered cubic iron or face-centered cubic iron. We talked earlier about how we can get different allotropes of iron if we change the temperature. Each of these would be its own phase. Okay? So even though the elements are the same, they're arranged in a different way, so they're different phases. We can also have an FCC phase, which is comprised of iron atoms. So maybe it's taking what used to be pure iron atoms, and we're mixing in nickel atoms in solid solution. That, even though it has the same structure, and most of the atoms are iron, is a different phase than pure FCC iron. There's lots of other examples, just a few other ones I want to mention. Another example would be something like nickel-3 aluminum. This is what's called an ordered metallic or an intermetallic. So this is something where it has one of those ordered chemical phases. We can also have things like liquid materials as well. So I could take nickel, and if I heat it up enough, it will melt and become a liquid. That's a phase too. Just to sort of show some examples of this, we've probably seen a lot of these things in our sort of everyday life. If you look and have an ice cube on a surface, you're actually going to see, if you zoom in enough, see the three phases of water. So you can have solid water and ice. You can have liquid water that's melting onto your surface. And then there will also be water vapor in the air. We can make solutions. So if we mix together water and alcohol, if those things mix, that's one phase, even though we put in two components. Another good example is if you put salt into water, you can, if you put in just a little bit, you can mix that fully in and get a brine. But if you put too much salt into a glass of water, you won't be able to mix it all. And what you'll end up is some solution. So it's salt water, but it's saturated. So it's the maximum amount of salt it can hold. And then you'll have excess salt that forms on the bottom. Okay, so in this case, we have two phases, that salt water and then that excess salt. Just to provide a counterexample, if we try to mix oil and water, they won't mix, unlike that water and alcohol. So they'll stay phase separated, and we have two phases. One is the oil, and phase number two is the water. We're going to often talk about this more in the context of solids, because that's what we make most engineering materials out of. And I just want to point out, these are three different examples of solid phases that are showing different things you can get from metals. So in the top left corner, this is nickel and copper. They're mixed together in a solid solution, but you can see that the atoms are sort of scattered randomly. So this would be a liquid. On the top right, it's the same types of atoms, but now they're on some ordered lattice. So this is a solid mixture of that nickel and copper. And then on the bottom, this is an example of copper and zinc mixed together. On the outside is a solid solution that looks like that nickel and copper solid solution. And then in the middle, some intermetallic or some metallic compound has formed. Okay? So one phase, two phases on that bottom picture. So solutions are just mixtures. It can be a solid, liquid, or a gas, but it's a single phase. It's when we're sort of blending things together. I use the wrong word because mixture really means we have more than one phase. Okay, so I want to show you a very simple phase diagram. On the y-axis, we have temperature. On the x-axis, we have composition. And this is for water where we're mixing in sugar. Okay, so 0% sugar means we're 100% water. 100% sugar means there's no water, it's just solid sugar. And this is a very simple phase diagram. Okay. Now, an important thing to point out on here is you can identify what's called a solubility limit. And this is just the maximum concentration for which only a single phase exists. So let's start out with that pure water and think about what happens. We'll just start out at some temperature. We'll start at room temperature. In this range, we have a liquid phase. So it's described here. And this is just a solution. So it's, you can think of this as a syrup. So we're adding sugar into the water. We can keep adding it. We're moving on this plot, but we're staying in that same region, which is labeled with that capital L, so that liquid. At some point, if we add too much, so at this plot, it's at 20 degrees C, it's something like 63% sugar. We'll no longer be able to have one liquid phase. Now we'll be in this other region of this plot. It'll be liquid plus some solid sugar. Okay, so that's that two-phase region. This blue line right here is denoting what's the maximum we can have in that one phase. So that's what we call the solubility limit, right? And you could go in and pick these things off, okay? And it tells you that as if you're less than that composition, you have just a liquid. And if you're more than that composition, you have a liquid plus a solid. Again, this doesn't have to be related to only sugar and water and these sort of, cooking examples. The same thing can happen when we mix together engineering materials. On this image right here, it's showing you a microstructure that's formed when we've mixed together aluminum and copper. Two phases have come out. This is actually imaged through what's called backscatter electron imaging. Basically, the contrast, the color, comes about because of the atomic weight. So the fact that we have a dark region and a light region means that one of these phases is aluminum rich and the other phase is copper rich. Okay, but it's the same type of idea. We've gone past that solubility limit and now we have two phases. So we can go back to that simple example of the sugar water and think about, we just talked about what happens when we change composition. Let's change along the other axis. So let's say that we started at this point A. We're at 20 degrees C. We have 70% sugar. So we're in the two-phase regime. We're liquid plus sugar, solid sugar. If we heat up that solution, in this case to about 100 degrees C, we'll find that we cross that boundary and go back into the liquid state. Okay. This is, again, something people know from cooking. If you want to dissolve more into water, you can heat up. Okay, it lets you do that. But the main point I wanted to point out is just like changing composition can shift where you are in this phase diagram, so can changing temperature. And you could think about moving around in different ways, okay? So even at 100 degrees C, if you add too much sugar, so if you increase the amount of sugar in there to 90, you'll go back to that two-phase region. So let's start looking at some more relevant phase diagrams, and we're gonna start with something simple. So we're gonna start with nickel copper. If you remember a few lectures ago, we talked about the Hume-Rothery rules. These are the rules that tell us if something will have a high solubility. And we mentioned that nickel and copper really hits these things. They have the same crystal structure, similar electronegativities, and similar atomic sizes. So these are actually what's called totally miscible, which means that we can form a solid solution from 0 to 100% of either element. So this plot right here is showing what a phase diagram would look like for this material. On this plot, it's still showing temperature on the y-axis, composition on the x-axis. This is a common choice, and most of the phase diagrams we see, those are going to be the chosen axes. But one thing I want to point out is that that's just an arbitrary choice. You could choose to plot something like pressure or other variables on these axes, and that would be a reasonable thing. And a good example of that is if you go and you Google a phase diagram for water, for example, it's very common to see a phase diagram showing temperature on the y and pressure on the x-axis, okay? And what we're really trying to do is just make a 2D plot out of a much more complicated space, okay? If you see a plot like this, where we're just showing two of those variables, it means all of the other variables are held constant. So this plot doesn't show pressure. So what that means is that pressure is held constant, and usually we do this at 1 atmosphere. So it means it's just whatever you would find out in the real world, in your lab, things like that. So this is what's called a binary phase diagram because there's only two components. There's copper and nickel. Again, this x-axis is described in terms of how much nickel I've put in. So if I have 0% nickel, that means my sample is all copper. If I have 100% nickel, it means it's all nickel, right? In this case, we can identify a few important ranges. So there's only two phases shown on this plot. So at low temperatures, our material is solid. At high temperatures, it's liquid. But this set of boundaries between these two materials is not even. And what that means is that nickel melts. So think about pure nickel goes from liquid to solid at a higher temperature than pure copper goes from liquid to solid. Okay? So along this straight line, this would be pure copper. This one would be pure nickel. Okay? So we end up with this sort of lens shape diagram. And interestingly, another thing I want to point out is that there's also another phase field, this one in the middle where you can have some mixture of liquid plus solid, okay? So if I'm up here, I'm all liquid. If I'm down here, I'm all solid. If I'm in the middle, I'm some mixture of those two phases. So this system is binary. It has two atomic components, copper and nickel. It's what we would call isomorphous. So it has complete solubility of one component in another. And if you look at that, means that there's just one type of liquid you can have and one type of solid. Those extend completely from 0 to 100%. And we can start to pick out a few important things we can do with a diagram like this. So the first thing we can do is that if we know what our temperature and our composition is, we then can read off of this type of diagram the number and types of phases present. So let's look at an example. If we say we're at point A, it's 1100 degrees C and 60% nickel, we can see we're in that solid solution region. So that means we have one phase. I'm giving that the label alpha here. If I'm at 1250 degrees C and 35% nickel, I'm in that two-phase regime, liquid plus solid, and I can move around and think about that. So that one's easy to see. The phase diagram is just telling us what is there. But this phase diagram also lets us figure out what the composition of each phase is in each of these cases. Okay? So let's take and look at a few examples. So if we are at 35% nickel, that line goes right there. And depending on the temperature, we can be in any of these three phase regimes. At a high temperature, 1320 degrees C, we just have liquid, okay? An important thing to do is what we're basically reading off of this is we know our composition of the whole material is 35% nickel. So we know that if we're in a single phase regime, we only have one option. That phase, the liquid phase, has to be 35% nickel. Okay, that's easy. We can go down to really low temperature, so 1190 degrees C. We're now in the solid phase, but we're still in a single phase region. So our only option is that one phase we have has to be the same as our sort of overall composition, 35% nickel. But the more interesting question is what happens when we're in this two-phase regime? So we're in this regime of 1250 degrees C. we know we have both a solid and a liquid phase. What we actually can do is use what's called a tie line to determine what the composition of each phase is. So we're at this point B. Our overall or global composition is 35% nickel. We can extend a horizontal line out and see where it hits each of these regimes. So if we extend it out, it hits the liquid regime at 32% nickel. That's going to be the composition that our liquid phase has. It can't have more than that. That's the sort of max it can have at that temperature. Do the same thing for the solid. So we extend out that line, we hit the solid phase, we see that it's at 43%. Okay, so our overall material, if I sort of zoom out and just measure chemically this huge box of material I have, it's 35% nickel. But if I zoom in, I see that I have a liquid phase with a little bit less nickel and a solid phase with a little bit more nickel. The third thing we can do is take advantage of the fact that we know what the composition of the individual phases are, and we also know what the overall composition of our material is, to then go and calculate how much of each of these two phases do I have. Right? So to do this, we can use that tie line again. So if we have 35% nickel, we can go and figure out how much of each that we have. And the idea is that those amounts just have to add up to be equal to the 35% nickel. The way we do this, and it's easy to see with this tie line, is if I want to know how much liquid is in there, I take the length of the other chunk of the tie line. Okay, so this is that line S, all right? What's the length of line S? It's easy to see. It's actually 43 minus 35. So it's 8 weight percent, okay? And I'm gonna divide the length of that line by the total length of this line, okay? And that's easy, again, easy to see. So 43 minus 32. So it's gonna be 11. We take that ratio, and this tells us that we should have 73% liquid, right? If we do that calculation for the solid side, again, we want to know how much solid. So we're going to take the length of the other side of the line, R, 35 minus 32, and divide it by the total length of that line. And we'll get 27 weight percent. The simple way to think about this is we know our overall composition needs to be 35, right? And we know that each of those phases has a different composition. Which one is closer to the overall composition of our whole sample? The liquid is. The liquid's only 32. That's much closer than 43 is, okay? So we know that we need to have more of that. That bears out from this calculation. Okay. Now, if we're in the single phase regime, it's super easy. So if we are only in the liquid phase, we know that it's 100% liquid and we don't have to do any of this calculation. Okay. So this tie line that connects this and that we can use to make this calculation is sometimes also called an isotherm. And that rule I just explained to you can be thought of as sort of a lever rule, or if you want to think physically in terms of something we're used to, you could think of it as like a teeter-totter, okay? So we want our average to be centered around that global composition. And this teeter-totter is much longer on the solid side because that solid phase has a lot more nickel than our average. The liquid is closer because the composition is closer, okay? So we're just sort of drawing that proportional to the length of these lines. And if I think about that as just if I have this teeter-totter and I need to put weights on it, I would need to put more weight on the shorter lever arm and less weight on this longer lever arm. So again, this is just describing sort of how we would do that calculation. We already went over this, so I'll leave it up there. But again, if we want to know how much, this is our mean or average composition. We want to know how much of this phase to the left. We take the length of the line on the other side and then divide by the total line length. we want to know how much of the phase on the right we have, we take the length of that opposite side and divide it by the total length. So we can think about what this means. So if we have a copper nickel alloy, maybe is at that 35% nickel, if we're at the high temperature of 1300 degrees C, it will be all liquid. As we cool it down, what we're going to do is we would pass through different phases of material. Okay. When we're at point B, so we're just in that two-phase region, we're going to have some mainly liquid with just a little bit of solid, okay? As we move down further, the amount of solid is going to grow. But the other thing I want to point out is that the amount of solid we have is larger, but also the composition is changing as our temperature goes down. Okay? If we get down near the bottom of that two-phase region, our material will be mostly solid with just a little bit of liquid in there. And then finally, if I go down into the solid range, I now have a solid structure, okay? So again, I just want to point out that different points within this are going to have different amounts of solid and liquid, but also different compositions of those solid and liquid phases. So you could be asked to go in and pick out at those different points. This is just another view of that and say, what are the compositions of the phases at each of those points? So at point A, the liquid has 35% nickel. That one's easy. We'll move to point B. So we can again pick out that we will have 35% nickel in the liquid, come over and see that we have 46% nickel in the solid. So again, we're just marking out where those levels are. Can look at that point in the middle at C, mark out what the composition of each of those phases are, and keep on doing this. Right? So one important thing to point out is that a phase diagram is really describing that under these thermodynamic conditions, so the temperature and composition here, it's telling us which phases are in equilibrium and what their composition and relative amount is, okay? But the important thing is that it only is speaking to equilibrium, okay? It doesn't tell us anything about how this forms. So for example, we'll talk about this a little bit later, but one thing that could happen is, what if you didn't give the system enough time for all the atoms to find their equilibrium positions, right? And let's take an example that's sort of between these two points, so between point C and D, right? If I move down in this range, okay, I could, right here, want to form solid phases, which are 35% nickel, all right? And my phase diagram tells me that at equilibrium, I'm gonna have a chunk of solid and it's gonna have 35% nickel. But imagine if I did this cooling really fast. So I came down here and some of my cooling happened up at the top and some of it happened at this intermediate range, and then some of it happened near the outside. So what I actually get is the middle of this is going to have a large amount of nickel because it first started becoming solid up here. And that amount and that sort of density or that amount of nickel you get is going to decrease as I come out in this particle, okay? We haven't yet talked about the tools to predict that or deal with that. I just want you to sort of understand that this is assuming that we sit at that given temperature for a long time and let everything equilibrate. So you could go and look at how this affects mechanical properties. So for the copper nickel system, it ends up being pretty clear because it's all a single, if we're in the solid range, we're all a single phase. So we could go and make solid copper nickel alloys that vary over the whole composition range. What we would see is that our tensile strength increases and then decreases. The points where it hits These axes are for the tensile strength for pure copper and for pure nickel. And those points in between are described by our equation for solid solution strengthening, which says that our strength goes up with the square root of composition. Okay. So in this plot, we would find a peak value of the tensile strength as a function of the composition. We could also go and look at the ductility. We mentioned how strength and ductility often are inverse of each other. And in fact, our elongation to failure would drop and sort of reach a minimum as a function of composition here. We could keep building up the complexity of these phase diagrams. That first one I showed you for copper nickel was very, very simple. This is a slightly more complicated diagram, but it's still a binary phase diagram. This is what happens if we have copper and we're mixing in silver, okay? So now we have a liquid phase. We have a solid phase for copper. We have a solid phase for silver, but in between, we have more transitions between those three different states, okay? So, but we can still do a lot of the same things. So we could go in and ask, so at 1,000 degrees C, what's the maximum solubility of silver in copper? So it's saying in this copper-rich phase, how much silver can I put in? I can still do the same thing. I can draw a line across at 1,000 degrees C. In copper means I'm looking at this high copper percent. I can trace a line along that boundary until I hit the phase boundary, and I can read off how much silver I can have in the system, okay? So I can do the same thing I did with that copper nickel and even the water and sugar type of examples. So I can say that the maximum solubility of silver and copper is 6 weight percent silver. One thing I want to point out is this plot, I showed you something that's very common. It's very common to have two x-axes. So you can have composition either in weight percent or atomic percent. We talked about how to convert between those. This example even has the temperature axes in degrees Celsius and degrees Fahrenheit. So you just want to make sure you're reading off, when you take a number, make sure you check the units on the where you took that number from. We can flip this question around and ask, what's the maximum solubility of copper in silver, right? So the way I ask that is I'm asking, if I start with silver, how much copper can I put into it at 600 degrees C? And I'm sorry, I was looking at the wrong axis. It's 600 degrees C, so I would need to be up at this line, okay? So how much can I put in there? I again come over and see where I hit that phase line, go down, and I could say, okay, well, I can put 4% copper into that silver lattice in solid solution. So this is actually what's called a eutectic binary phase diagram. And that special word just means that there's a point on this phase diagram where a liquid is in equilibrium with two solids. And that point is marked E right here. So this is where that liquid meets at a point, a two solid phase regime. So there's two solid phases, one that looks like the copper rich, one that looks like the silver rich, and they meet that liquid phase. Okay, so that means as I heat or cool, I could have that transition from two solid to liquid or liquid to two solid. And again, just a reminder that alpha is designated, it's a FCC phase of copper with maybe a little bit of the silver mixed in as a solute. The beta is a face-centered cubic silver with maybe a little bit of copper mixed in as a solute. Yeah, so again, just a binary eutectic means two components and has that special point where the liquid meets the two solids. You can think about this as that's the minimum melting point T, okay? So this copper-silver phase diagram, it has three single phase regions, one liquid and two solids, alpha and beta. It has limited solubility, so the alpha is mostly copper and the beta is mostly silver, and it doesn't go to large amounts. There's no liquid below this eutectic temperature. So no matter what my composition is, if I'm at that, I'm below that temperature, I'm solids. And you can look at this C sub E, this would be the eutectic concentration. This tells you what composition or where that eutectic temperature lies on this plot. What's the X location of it? Okay. And if we look at the details of this, we can pick out what the compositions of the different phases are. So at that eutectic point, our liquid, which is 71.9 weight percent silver, would want to change into two solids. And those solids are going to be a solid alpha with 8% silver and a solid beta with 91.2% silver. So we'll start asking ourselves some questions. So let's say we have, this is a different binary eutectic phase diagram. This is for lead tin. So it looks very similar. The exact points where the lines hit are a little bit different. You could be asked to determine the phases present for a given set of conditions. Let's look at 150 degrees C. And for 60% lead and 40% tin. So we'll come at 40% and see where we meet up with that temperature. We can look in here and notice that we're in that two-phase solid regime. So the answer is we have two phases and they're out, and it's alpha and beta. We can also ask ourselves, what are the compositions? So if we move over to the left, we'll see that the alpha has 11 weight percent tin. The beta has 99 weight percent tin, so it's almost all tin. We can also ask the relative phase amount. So how much alpha do we have? Okay, remember, it's the length of the other line. So S, 99 minus 40, which is 59, divided by the total length of this, which is 99 minus 11, which is 88. If we do that math, 59 divided by 88 is 0.67, or about 2/3 of the material is going to be alpha. We could subtract and find that the other 1/3 is beta, but if we want to do a sanity check, we could rerun that calculation. How much beta do we have? Take the length of the opposite line and divide it by the total line length. We could keep doing this for different temperatures. So in this case, we've raised our temperature to 220 degrees C. We again can go and pick out that point. In this case, we find that we're a liquid plus a solid of the alpha phase. We can again mark out where the compositions are. The solid alpha phase is 17% lead or tin. The liquid phase is going to be 46% liquid. We can go and figure out what are the relative amount of the phases that are present. So in this case, this line is closer to the liquid, so we have more liquid. The length of that line divided by the total length tells us that we have 79% liquid. Okay. So we can think about what the microstructures look like. We're going to look now first at sort of below that 2 weight percent tin, and this is where we're in the solid solution range for that whole thing. We don't hit into the two-phase solid range anywhere in there. And our material we're going to get is going to be a polycrystalline material with grains of alpha phase having a composition of 2 in this case. So that liquid, it's liquid at the beginning, it's solid at the end, and in between, it's these solid phases growing out of that liquid. We can move over a bit on this phase diagram. Now we're going to be between that solubility limit at room temperature of 2% and at that solubility limit at the eutectic temperature. So we're going to be in between that. We'll start out as a liquid again. We move down to the 2-phase region. We have some solid alpha particles that grow. When we're in this range at 200 degrees C, we are only alpha phase. As we keep moving down, within that solid phase, some beta phase will come out, okay? And again, we have alpha plus beta at that lower temperature. Keep on doing this. Let's think about what happens right at that eutectic temperature. And this is important because you actually get a quite interesting structure. So in the liquid, we have a liquid at 61.9%. In the solid, we have alpha plus beta, shown here by white and red lines. and we can pick out what the composition of each phase is and how much we have. But what's interesting is when you come down and cool at this eutectic point, you again end up with crystals of different orientations, but they often have this striped type of pattern. And this is a real life micrograph of a lead tin microstructure. And the reason this forms is pretty interesting. And it just comes down to the fact that this composition needs to go locally from 61.9% to some mixture of a very low amount of tin and a very high amount of tin. So the way it actually does this is it forms this, what's called a eutectic lamellar structure. So as the solid grows, it doesn't grow one big chunk of lead and one big chunk of tin. It grows a chunk of solid, which has this striped type of pattern. So the extra lead gets pushed over to the alpha phase. The extra tin gets pushed over to the beta phase, and these striped regions grow. And that's why you end up getting those different crystals with which within them you have these stripes. We could keep thinking about different possibilities. If we're on the left of that eutectic, we'll go from a liquid to a little bit of solid. As we decrease the temperature, the solid grows. And right before we hit and cross that eutectic temperature, we can calculate what's the composition of the solid and the liquid and how much we have. In this case, I chose it so that it's 50% solid, 50% liquid. Now, at that point, when we go right below that, all the liquid needs to immediately turn into two-phase solid. So all these regions that were green turn into that striped region. But what I want to point out is those original chunks of blue alpha phase still exist. So they have a different composition than the blue alpha phase in the second region. So sometimes this is labeled as these regions which first formed by themselves are called primary phases. So this is a primary alpha phase. And then this striped section that formed is called eutectic alpha and beta. Okay? And it forms at this specific composition, right? 18% for the blue phase and 97.8% for the red phase. So again, just pointing out that even for this phase diagram, and all that this phase diagram tells us is sort of what the relative amount of alpha and beta will be. But if we move around on different regions, we can get different types of distributions within space. So right at that eutectic point, we have crystals with these striped patterns. If we move to the left, we have those crystals with the striped patterns. Then there's also these big blobs of alpha phase mixed in there. So if I zoom into that eutectic microstructure, it looks the same as this part, but there's these big blobs of alpha. If I'm on the right side of this, I see something similar. Again, eutectic phase everywhere, but there are these big blobs of primary beta phase. Another important sort of next step up in the complexity is we can, in addition to just having a solid phase all the way on the left or all the way on the right in our pure materials, we can have an intermetallic compound somewhere in the middle of this plot. Okay? This exact one is showing an intermetallic compound for magnesium 2 lead 3, or sorry, magnesium 2 lead 1, which means that we have 2/3 magnesium. If you need to do a sanity check, this is some different number for weight percent, but for atomic percent, that would be at 33% lead. Okay? This is also a good example because lead and magnesium have very different atomic weights. So magnesium is very, very light, lead is very, very heavy. So this weight percent and atomic percent scale are very different. Okay? So 1/3 lead in terms of the number of atoms means that 80% of the weight is coming from the lead. Okay, so it's a really heavy atom. In this case, this intermetallic exists as a line on this phase diagram. So we can only form at this one composition because it needs to have this stoichiometry, this fixed value of the composition. So we can think about some of those three-phase reactions that we can have. We already mentioned a eutectic. So this is where a liquid can go to two solid phases. There's lots of other examples. We can have what's called a eutectoid reaction, and this is when one solid phase goes to two other solid phases, right? So lead tin had this eutectic. An example of a system that has eutectoid, and we'll see this in a little while, is the steel phase diagram. So steel can go from FCC to BCC plus some intermetallic that has a special name, cementite. But there's many other options. So what's called a peritectic reaction is when a liquid and one solid phase transform to a second solid phase. And what I did is sort of, this plot right here is showing you some of these different options. So this is our eutectic. A liquid becomes two solids as we cool. This is a peritectic. A liquid plus a solid becomes a different solid as we cool. Monotectic is where a liquid becomes a solid plus a different liquid. Eutectoid, a solid becomes two different solids. And then peritectoid is two solids become one different solid. Okay, so eutectoid and peritectoid are sort of flipped. A good example of this is the copper zinc phase diagram. So this is showing what's the temperature versus weight percent. So zinc melts at a really low temperature. So it is way over here. And there's this large liquid regime right here. So as we were moving across, we could go from liquid to solid, even at the same temperature. And we could hit these different solid phases inside of here as well, okay? So this has a lot of those different features. If we zoom in and look locally, we see that we're going from one solid to two different solid phases. That's a eutectoid reaction. At the top of that, we also have a peritectic reaction. We're going from a solid plus liquid to a different solid. We can find different options. So this is an example of the well-known steel phase diagram. We can identify a few different points. There's a eutectic, so we're going from a liquid to two solids at that point A. There's also a eutectoid, where we're going from a solid to two different solids at point B. Okay, so if we think about what happens if we're above that temperature at point B, we only have this one solid phase. This has a specific name called austenite. If we're down below that point, we are going to have two solid phases, something which is called ferrite. So this is body-centered cubic iron plus cementite. So it's some ordered compound, iron 3 carbon. And a real microstructure is shown here on the left. This is actually so common that this mixture of these two phases is itself given another name. This is called perlite, alternating layers of alpha iron and this iron 3 carbon cementite phase. Okay. So it's really common. We actually want to give it its own name. So this is just showing a different view of as we move through that eutectoid reaction, how we can get interesting different microstructures. That reaction that happens in the solid phase transformation is very similar to what we saw in the eutectic. So that liquid, which has a given composition, needs to very quickly change into a solid with one composition much less and one composition much more. That same thing happens at this eutectoid reaction. So that austenite phase, which is solid, needs to quickly turn into two different phases. One, which has a composition way over here, and the other one, which has a composition way off to the right. So it again forms that striped type of pattern, right? And what's important again is we talked about thinking about primary versus the eutectic microstructure. The same thing can happen in the solid-solid phase transformation. So I've shown two examples. Let's move along this line on this left plot. So we're solid gamma phase. As we move down into this regime, we'll have a little bit of that gamma, but we also will have some of that alpha phase, okay? And those are those orange blobs that are shown in here. Those could theoretically come up anywhere. What we will talk about when we dig into phase transformations a little bit more is that it's usually easier for these to start at some defect. So they're shown starting at grain boundaries, okay? And they sort of cover that eventually. Now, when we transition across this eutectoid temperature, So whatever remains of that gamma phase needs to immediately transform into the alpha plus cementite phase. These regions, which are gray here, transform to the striped regions. Okay, so we have striped regions that are blue and orange, and then we have the pure orange regions. Those blue and orange stripes, those are that perlite that we mentioned. And that region right here, you could call this some primary alpha, but a more common name is pro-eutectoid alpha. It means the alpha that formed before we went through that eutectoid composition. Okay. I want to do that same sort of thought experiment, and instead of being on the left of that eutectoid point, we're going to move to the right. So let's come down up here. Up in this range, we're still just one solid phase. We move down into the two-phase regime. We want to form a new solid phase. It's not the orange one now. Now it's the iron 3 carbon, so the cementite. We're drawing that as a dark blue or a purple. So this dark blue wants to form. Again, I'm drawing it forming at the grain boundaries. Right when we transition across that, these gray regions need to now become striped regions, okay? So we have striped regions, which are that perlite, and then we have blue regions by themselves. So these are what you call pro-eutectoid cementite. They formed before we went through that eutectoid transformation. So let's do sort of a quick sanity check. What's a eutectoid and what's a eutectic? They're very similar. We're going from one phase to two solid phases. The only difference is what we start as. So the eutectic is when we start as a liquid, and the eutectoid is when we start as a solid. Okay, so our end result, we have two solid phases. Eutectic, we start as a liquid. Eutectoid, we start as a solid. I want to point up another time that virtual material science and engineering tool is helpful. If you want, you can go and access interactive phase diagrams. Let me come out of my slides real quick and show you how to do this. So if you go to Wiley Plus, click on MSE, I'm going to go to phase diagrams. You can go and pick out a few different examples. So this is a simple isomorphous phase diagram. I can move around at different places on this plot. And as I do that, on the left, it will show my microstructure. So if I'm all the way on the left, I am going to be pure, this is lead antimony bismuth. I'm pure antimony. If I go to the right, I'm pure bismuth. And as I move over, I can see I can form a solid solution in either of these cases. One of the differences is that at this temperature, the antimony is solid, the bismuth is liquid. So you see just no microstructure there, versus in the solid, you'll see some grains. In this intermediate range, I can start to see that my material is some mixture of liquid plus solid. And those solid and liquid regimes do not have the same composition. And this will do those calculations for you. You can also go in and play around with eutectic type of microstructures. So in this case, they're trying to get you to move along different lines of a given composition. So we're a liquid here. It's showing sort of random fluctuations. And as I come through, my material solidifies and it has that given composition. We can contrast that with what happens if we're before that eutectic point. So I'm going from liquid to solid. So there's really little solid points. So these are solid. They're alpha, so they're mainly red. And as I keep going down, they grow until right before, these are solid, these are liquid. That liquid is going to quickly need to change into that eutectic microstructure. So it forms that lamellar or striped pattern. That's kind of helpful to play around and see how those work if you're interested. All right, so I think that brings us to the end of today. I'll see you soon in a Q&A session. So good luck studying and checking out this introduction to phase diagrams.